Hello everyone, my name is Afdhal and I want to present my paper about modeling of the thermomechanical effect on geothermal well injectivity. This is the outline of our presentation. First, the reinjection is one of the most critical aspects of geothermal management. So, understanding about the reinjection system is essential to improve the resource management. During the geothermal well completion test, the injectivity can be calculated to determine the necessity for injection well. The formation temperature surrounding the wellbore decrease due to the drilling and injection of cold water during the completion test. And the cold fluid causes the rock contraction, resulting the bigger pore space and increased permeability. Meanwhile, when a hot fluid is injected during the operation stage, the rock matrix expand and contract, narrowing the pore space and potentially reducing the permeability as well as injectivity. This study aims to make sectoral numerical modeling and to study the effect of temperature changes on well injectivity using the CMG STARS simulator. After the drilling activity, a series of completion tests are carried out. This test aims to identify the depth of the main feed zone in well to optimize the need for well intervention and help to predict well performance from its injectivity. First, the water loss test or PTS injection test aims to identify the location of permeable zone or feed zone in the well. The ratio of production flow rate to pressure drawdown at the midpoint interval of the production zone is defined as productivity index or PI. Then the multi-rate injectivity test was carried out to obtain the injectivity index or II to estimate the injection capacity and maximum mass flow rate of the well. A previous study by Zarok and McLean provides a qualitative relationship between measured well injectivity and production potential in two-phase wells. However, high injectivity does not always indicate a good productivity. The well must also have sufficiently high feed zone temperature. After the multi-rate injection test is completed, a fall-off test or FOT is performed by recording the bottom well pressure after the injection is stopped to estimate the permeability thickness or transmissivity and storage coefficient or skin. So what is the effect of temperature changes on well injectivity? By injecting a fluid with a temperature that is hotter or colder than the formation, the feed zone's temperature changes, which have an impact on injectivity value. The injectivity may decrease as the injection heating up the formation and may rise as the injection cools the formation. Based on observation made at Wairaki Tauhara geothermal field by Saga, Saga developed an empirical technique to adjust the injectivity of the fluid injection temperature. The completion test data after drilling and injection data from 21 injection wells in 3 different areas in Wairaki Tauhara field were then analyzed to observe changes in injectivity. The result of a study conducted by Saga shows that the relationship of changes in injectivity to changes in formation temperature. As seen in this figure, it can be concluded that the effect of temperature changes on formation is very sensitive to changes in injectivity. And then the injection into the geothermal reservoir causes formation damage. resulting a decrease in permeability around the wellbore. Miadogne and Amadou then derived the equation for the relationship between temperature and absolute permeability in porous media by making a mathematical model in the thermal effect as described in this equation. The numerical model was developed utilizing a number of factors in geothermal field data. Then the conceptual model and well data of X geothermal field are used in this model as reference data. The reservoir is situated in high terrain topography with a liquid-dominated geothermal system and fracture control reservoir, according to this conceptual model. And this is the illustration of a grid in the model by using CMG stars simulator. The model consists of 22 layers, with the thickness of each layers are shown in this table. And this figure shows a cross-sectional illustration of the materials distribution of permeability and porosity of the model. The simulation sets the final time with a maximum of 800 years in order to achieve natural state condition. After 300 years, the simulation process approach the natural state. These figures display the pressure and temperature in the natural state condition. The pressure and temperature result in the model are then plotted against the pressure and temperature data of the well. This is shows the pressure and temperature plot of the model matching with the field data. So then the model can represent reaching the natural state condition. Then the pressure and temperature data are taken for the simulation at the exploitation stage. Then the injection simulation was carried out by injecting cold water at 20 degrees Celsius, assuming an injection rate of 1,200 gallon per minute at a constant injection rate. The injection simulation result shows difference in the pressure, temperature, permeability, and porosity distribution over time. There is an increase in formation pressure after injection, as you can see in these figures. However, due to the cold injection at a temperature of 20 degrees Celsius, there was a decrease in the formation temperature. The simulation result of permeability and porosity in the model are shown in these figures. It can be seen that there is a trend of increasing permeability after cold water injection with a percentage change about 4.6% until 42.8%. Meanwhile, porosity is also increased with the percentage change about 1.4 until 13.9%. Based on the water loss test performed during the completion test on the well, as a result, it is shown that a shut-in well has fluid flow from the upper feed zone, which is considered at a depth 860 meter inflow, to the lower feed zone, which is at a depth of 990 meter outflow. The details of the injectivity calculation are shown in this figure. Using mass and heat balance analysis, the upper feed zone productivity index at depth 860 is 2.8 kilogram per second bar, and the lower zone productivity index at depth 990 meter is minus 16.8 kilogram per second bar. The negative value of productivity index in lower feed zone indicates that the direction in the which the injection fluid flows into the formation. The analysis result indicate that the main feed zone is at a depth of 990 meter with an injectivity value is 16.8 kilogram per second bar. Based on the injection simulation result on numerical model using CMG star simulator, it can be concluded that the injectivity calculation of injection 1 well was carried out shortly after rock properties such as porosity and permeability in geothermal field has been increased due to the cold water injection. This is consistent with other research that found that the expansion of the formation rock matrix and the lowering the formation temperature caused by cold water injection increase porosity and permeability as seen in this model. As a result, the calculated injectivity value for the well is higher than the actual injectivity value under natural conditions. So the conclusion is the thermomechanical impacts of rock have been implemented into the sectoral numerical model of the injection well in geothermal field X. It is clear that the geomechanics of the rock formation near the injection change as a result of the temperature and the injection fluid. The formation permeability parameter increased by 4 until 42%, and the porosity increased by 1.4 until 14%. Following the injection of water at a constant rate 1,200 GPM for 10 days. Calculation of the injection well injectivity is 16.74 kilogram per second bar with the feed zone depth at 990 meter. Because of changes in rock properties, the estimate injectivity value following the cold water injection is higher than the actual situation. In order to continue this study, it is important to evaluate the injectivity during the heating up period and the operational time when the water is injected at a higher temperature in order to observe variation in injectivity as a result of different injection temperature. This is the reference that we use in this study. Yeah, thank you for the your time and attention. Goodbye.
Good afternoon, panels. In this occasion, we would like to present our paper submission under the title Comprehensive Assessment for Enhanced Geothermal System or EGS in South Sumatra Basin with Analytical Hierarchy Process or AHP as a recommendation for Prospeceted area development. This paper is written by 5 authors from Universitas Gadjah Mada. The first one is Alfu, Afkar, Annifari, and then Rania, Jasmine, Saeful, Ghofar, Zamianie, Putra, Aurellia, Anindita, and me, Radista, Saga. Ladies and gentlemen, the excessive in population growth has led to immense of energy demand, especially in Indonesia. To fulfill the demand, geothermal energy is currently creating a breakthrough primarily in its development in Indonesia. To maximize the potential, we conduct mapping strategy regarding selection of enhanced geothermal system, primarily in South Sumatra Basin. The basis of our basin selection is from the high resources potential and total geothermal resource. Despite its high potential, the reservoir rock in South Sumatra Basin are consist of sedimentary and also crystalline rock under the depth of 2,600 until 4,600 meter. Panels, in this study, we conduct a screening study first, then continued with the area analysis with the result of selection of Prospeceted basin. In this stage, we also divided into 3 main parameters, such as heat characteristic, geological condition, and socio-environment, with the subparameter as we can see on the slide. We use analytical hierarchy process with a 4-level hierarchy framework. For main criteria are assessed to bulk weight of criteria through the judgment. The weighting process, the consistency ratio obtained is below 0.1. Then after conducting weighting of each criteria, the alternatives are evaluated to generate the final recommended zone for developing enhanced geothermal system in Indonesia.
Ladies and gentlemen, following the previous slide, there are three parameters used for the site selection. And the first one is heat characteristic that consists of three sub-parameters, that is thermal conductivity, heat flow, and also geothermal gradient. In South Sumatra Basin, the heat conductivity is within the range of 1.97 watts per meter until 2.27 watts per meter, and the values are higher in the eastern part of the basin, like in the grade 4G, 4H, and also 8G. The geothermal gradient in South Sumatra Basin is also higher than the average values of geothermal gradient in other basins in Indonesia, which is more than 33 degrees Celsius per kilometer. And from the figure on the left, it is seen that the higher geothermal gradient value is concentrated in the landward or in the western part of the South Sumatra Basin. Meanwhile, heat flow value in this basin is spread evenly and also lowered in the eastern part and also the southeastern part of the basin. Ladies and gentlemen, the second parameter is geological condition that consists of two sub-parameters, that is depth and lithology and also lineament density. And reviewing from the structural geology will assist the assessment and also evaluation on stress condition on the research area. And the geological condition sub-parameter of depth was determined by the 29 available wells data of temperature recording depth, and in application of enhanced geothermal system, it is preferred in having conducted rock depth below the 5,000 meter below the surface, and also the linear density was delineated based on the SRTM dam data of the related area. Well, ladies and gentlemen, based on the figure on the slide, it is seen that the lineament delineation is denser in the southwest to northeast part of the basin, and the lithology of each grid can be seen in the table below. Well, ladies and gentlemen, this study also used conservative area as one of the sub-parameters for the socio-environment parameter assessment to consider the possibility of further developing of the resources. And areas that overlap with existing conservative area have a lower chance for the further enhanced geothermal system development. And also, the enhanced geothermal system is more likely to be associated with the lesser population density.
Ladies and gentlemen, our objective is to select the best recommended zone for developing EGS or enhanced geothermal system in South Sumatra. We use the analytical hierarchy process combined with the sensitivity analysis to perform the decision making. Analytical hierarchy process is a powerful decision making tool where logical, intuitive, qualitative, and quantitative aspects are involved. It simplifies a multi-criteria decision making problem into a structured framework. The priority of each option will be obtained by quantifying the relative importance of each criteria. We perform the analytical hierarchy process with the aid of superdecision. As we mentioned it before, the first step is building criteria hierarchy framework. Continued with the judgment of relative importance of each criterion through pairwise comparison. Afterwards, we have to check the judgment's consistency based on the value consistency ratio. The judgment is acceptable if CR or consistency ratio is less than 0.1. Then compute the option priority and finally perform the sensitivity analysis to test the result robustness, whether small changes in the pairwise comparison judgment will affect the final priority result. The consideration criteria involve are heat characteristic, geological condition, and socio-environment. The criteria are developed further into four-level framework, where each criterion is divided further into sub-criteria under socio-environment. There are land use and conservation area, and also population density. And then under heat characteristic, there are heat flow, geothermal gradient, and conductivity. And last, under geological condition, there are lineament density, depth, and lithology. After the pairwise comparison are performed, the relative importance of each criteria is obtained. We obtain the heat characteristic is the most important criteria, and it is important to note that heat characteristic in this field could affect the other parameters significantly in the enhanced geothermal system. Therefore, the characteristic is strongly related to geological condition too. The next most important criteria sequence is also geological condition, then socio-environment parameters. Panels, to accommodate potential judgment scoring changes due to subjectivity, we also evaluate final priority ranking result to respond to the shifting in the weighting process. So here we perform sensitivity analysis in every alternative by increasing and decreasing the weight of each criterion. And based on some modification that we can see on the graphic scenario, more and more we get the result that zone C become the most probable recommended zone in South Sumatra to be developed.
And gentlemen, based on the previous statement and also explanation from our partner, that is Saga, we can conclude 4 points. That is, first, the zone C becomes the most probable area for enhanced geothermal system development because it covers all the parameters used for AHP, that is social environment, geology, and also heat characteristics, with a 4-layered hierarchy process that we have already conducted before. And also zone C is also structured by the shale lithology that supports the process of burial process that will generate the heat source, and by the increasing of the sediment depth and also the thickness. And panels, the high heat flow value of the selected area, that is zone C, that is also comprising of grid 5C and its surrounding area, occurs either because of the highly radioactive component in there or having a thinner earth crust than the other area. And well, the grid 5C has the highest enhanced geothermal system possibility area to be developed, analyzed by our analytical hierarchy process that we have already conducted. Well, that's all from our presentation paper submission. We hope that this paper will be valuable and also will be useful for the further research. Thank you very much.
I, Yushantarti, and my partner Dudi will present the early chemical characteristics of geothermal surface features of Mount Lompobattang-Bawakaraeng, Goan Benteng Regency, South Sulawesi, Indonesia. Where is the area? This is the location. There are about 70 kilometers from Makassar city and 25 kilometers from the Regency capital of Goa. And this is the image location from Google Earth. We can see the Mount Lompobattang and Bawakaraeng. So the geological data is gathered in 2018. It shows that the stratigraphy of the Lompobattang-Bawakaraeng geothermal area is composed of the oldest rock in the form of tertiary marine sedimentary rock consisting of limestone and sandstone. After the deposition of this sedimentary rock, magmatic activity occurred which formed intrusive rocks with trachytic composition, which were exposed to the north of the Pencong Warp Spring. So this is a Pencong Warp Spring. Tertiary magmatism activity continued until the end of the tertiary or Pleistocene period, which was marked by the presence of batu rape volcanic products consisting of andesitic basaltic lava rock and pyroclastic rocks with the eruption center estimated to be located in the west offset of the geothermal area. So during the Quaternary period, tectonic activity occurred in the form of uplift, which was followed by pre-Lompobattang volcanic activity, namely Sapea volcanism. The product of Sapea volcanism are scattered in the north of this area, covering units of tertiary volcanic and sedimentary rocks. After Sapea volcanism, magmatic activity shifted to the east by forming the first phase of Lompobattang volcanic activity in the form of lava and pyroclastic rocks. The first phase of Lompobattang volcanic activity ended with the formation of parasitic cones at the southern foot of Mount Lompobattang. Lompobattang volcanic activity then continued at the Lompobattang main eruption center, producing andesitic lava and pyroclastic rocks, offering most of the first Lompobattang volcanic products. Volcanic activity also took place outside the main eruption center in the form of parasitic volcanism on the west slope of Lompobattang, forming the Rapo Lembah Parasitic Cone. Lompobattang volcanic activity formed a caldera structure at the top of Lompobattang with openings to the east of this area caused by presence of material fluids in the earth after the eruption, resulting in a collapse or depression. Lompobattang volcanic activity ended with the formation of the Bulu Porong lava cone, which is thought to be lava plug that formed in the middle of Lompobattang caldera. Active tectonic activity that took place in the geothermal area caused a collapse or landslide along the fault line that formed colluvium deposits on the northwest slope of Mount Lompobattang. Colluvium deposits, which are deposits resulting from the breakdown of previously formed rocks, are scattered to the west and northwest of the foot of Lompobattang. The geothermal surface features. There are two groups geothermal surface features. It is Lompobattang group surface features. They are consist of warm spring batu belerang and acid crater Lake Biru Raya. These two surface geothermal features is at the high altitude of this area. The second group is Pencong group. Only consists warm spring of Pencong and warm spring of Lama. So the geothermal surface features that are still active only warm spring Batu Belerang and Pencong Paranglo group warm spring. Whether the cold acid crater Lake Biru Luraya is not still active anymore. This is the physical characteristic of the surface geothermal features. The Pencong and Paranglo have the water temperature about 35 until 49 degrees Celsius. The pH are tend to be alkaline and the conductivity is 300 microsiemens per centimeter, and they have low flow rate. Whether the Batu Belerang warm spring, the temperature is only 31 degrees Celsius, but the air temperature is 18 degrees Celsius. So there are about the difference 10 degrees Celsius between the water temperature or the warm spring and the air temperature. But the conductivity, if compared with the Pencong group, is a little bit higher. It is about 1,835 microsiemens per centimeter. But the flow rate is very low. It's about 0.01 liter per minute. And then this is the water analysis result. We can see that warm spring of Batu Belerang, which is located at an altitude about 1,400 meters above sea levels, has dominant sulfate around 770 milligram per liter, followed by concentration of bicarbonate around 300 milligram per liter, chloride 18 milligram per liter, and silica around 73 milligram per liter. Whether the warm spring of Paranglo and Pencong has only lower concentration, but they have more dominant bicarbonate concentration rather than the other concentration. And the cold water Lake Water Biru Luraya only have a dilute concentration, but dominantly has sulfate about 13 milligram per liter. The triangular diagram of chloride, sulfate, and bicarbonate shows that Pencong 1, Pencong 2, and Paranglo 1 and Paranglo 2 warm springs are bicarbonate. This manifestation can be a reservoir fluid that has undergone a lot of mixing with surface water. The concentration bicarbonate of the Pencong Paranglo warm spring was around 146 until 172 milligram per liter. While Batu Belerang warm spring is plotted at the sulfate type, based on relative of chloride lithium boron triangle diagram, the Pencong group is in the boron zone, while the Batu Belerang is in the middle of the chloride boron zone, with values are not too high. Based on the result of this comparison and adjusting the result of geological data, the tendency of the geothermal system to be in the quaternary volcanic lithogy environment for the Batu Belerang warm spring, and for Pencong Paranglo warm spring, they are tendency to be the sedimentary environment. Based on the chloride boron ratio to determine the common source reservoir in general, from this triangle, we can decide that could be there are two geothermal systems, namely Batu Belerang geothermal system and Pencong geothermal system. For the NIK MG triangle diagram, is principally used to develop one spring condition as the end of the result of two processes that occur during the journey of the reservoir fluid to the surface. So we can see that the Pencong group, Pencong and Paranglo, is plotted at the lower boundary of partial equilibrium zone, while the Batu Belerang and cold water of the acid crater Loraya or Biru Lake or Blue Lake are all in the corner of magnesium or immature water zone. It can be concluded that the interaction between the hot fluid and the rock below the surface has resulted in the fluid with new characteristics that is the result of the process of some of it contained in the rock with the constituent elements of the hot fluid. It can indicate dilution or mixing with large surface water, especially in the warm water. For the water isotope deuterium and oxygen, it's so that Pencong warm spring and Paranglo warm spring could be the true geothermal fluid from a low temperature reservoir, so that the intensity of water and rock interaction in the reservoir is not significant. And it concluded by the value of the isotope water. We move to the next slide about subsurface temperature. The temperature of natrium kalium cannot be used for Batu Belerang warm spring or Batu Belerang geothermal system because they are at the immature zone water, so it cannot be said that the warm spring of Batu Belerang is originating from the reservoir. If we try to reflect the shallow part of the reservoir temperature, maybe we can choose the silica geothermal thermometer. It is about 120 degrees Celsius, but it is only reflects the temperature in the shallow part. So in the consideration for the geothermal system of Batu Belerang, it's from the geological setting of Lompobattang, which is a quaternary volcanic area where the heat source is still sufficient to form a geothermal system, with manifestation condition located at the high terrain. The presence of belerang or sulfur deposits and bubbles in warm water it still exists and strong. Batu belerang, which is quite intensive, reflect the gas below the surface, still strong enough to reach the surface. So it's possible that the reservoir temperature at the Batu Belerang geothermal system could be greater than 120 degrees Celsius. While Pencong and Paranglo geothermal system, it could be from the shallow of the reservoir geothermal system. We can decide that the calculation results from the reservoir temperatures are around 124 with silica geothermometer calculation, or around 139 with NAK calculation given by. So this is only early surface characteristic. We must have the next methods for the advanced to have a good interpretation on the geothermal system in Lompobattang-Bawakaraeng. The conclusion: surface geothermal operations in Lompobattang-Bawakaraeng can be separated into two groups, namely Pencong group and Lompobattang group, with the manifestation temperature ranging from 17 until 49 degrees Celsius appears in tertiary volcanic environment or batu rapi volcano. While in the east, it is in a quaternary volcanic environment, Lompobattang volcano, with its bedrock or basement, a tertiary sedimentary rock. The type of manifestation of batu belerang are in steam-heated sulfate zone, also and immature waters in the magnesium corner. And the type of warm spring Pencong and Paranglo in the bicarbonate zones tend to be in the lower limit of the partial equilibrium zone. The reservoir temperature is estimated to be around 124 and until 127 degrees Celsius by geometry given by silica, including the low and medium temperature. To find out the geothermal resources in this area, it is necessary to do other methods such as geology, geochemistry, and geophysics in more detail. So that's from us. Thank you.
Okay. Good day, everyone. I hope everyone can see my slide in the slideshow. Assalamualaikum warahmatullahi wabarakatuh. Good day, and my name is Arthur G. Penayawan. I am researchers from the Geological Engineering Department, Trisakti University. And in this great day, we are present our research about the upflow-outflow zone identification based on geochemistry indicator and flow fracture density correlation in Mount Gede. And I hope everyone and we can have a good discussion in the later Q&A session. And just enjoy the slideshow. Okay, as you can see, this is my introductions, the background, why we did this research, why we choose these topics. We know that the Java is a big island in Indonesia that have a big geothermal potential. And one of its province, the West Java, has geothermal natural resources with a total geothermal potential of 5.839 megawatts. And one of its geothermal area, it's the Mount Gede Pangrango geothermal working area. And from Fadila et al. 2013, we know that the detailed preliminary survey has not been carried out at Mount Gede Pangrango, but some later after this, in the letter, there are many researchers have conducted research in the Mount Gede Pangrango, but not in Mount Gede, in the Mount Pancar. And this indicates that geothermal investigation on Mount Gede are still very few and need to be developed. So we are doing a research in this area about the geothermal outflow zoning in the Mount Gede. And this is our research area. As you can see in the right side of the slide from the ASDM1 map. Okay. Next is the methods. There are two primary methods we are using in this research. The first is geochemical indicator analysis to determine the genesis and process and also the characteristic of the geothermal manifestation from the chemical element. And then the fault fracture density analysis to determine the condition and the characteristic of the microstructure in our research area to know about the geothermal fluid flow. And then the final result is we can delineating the upflow-outflow zone of the geothermal in the Mount Gede. And then we have some hypothesis that the geothermal outflow zone in the Mount Gede is most likely in the crater area or the center of the body of the volcano. And this is the figure of the research flow chart we are using in this research. Okay, this is just a brief explanation of the geological indication. Geologically, Mount Gede Pangrango is dominated by volcanic rock, and which are the quaternary rock periods with two different eruption sources, namely the Gede volcano and Geger Bentang or Megamendung volcano. And the important point is that the Gede volcano eruption was younger at the age of the Holocene epochs. This means that the Mount Gede have a good hit and become the geothermal resource in the future. And the lineament from the hillside map illustrate that the research area influenced by fault geological structure from the volcanic activity, and morphologically, Mount Gede is stratovolcano that indicates the composition magma forming from the intermediate volcano based on the Wachlich and Heiken classification. Okay, and then this is the fault fracture density analysis. And as you can see, this is the figure that from our result from the fault fracture density analysis and interpolation. As you can see, the lineament in our research area dominated, the direction have dominated to southwest to northeast direction. And as you can see, we divided two units from our FFD map. The first is the high fracture density area, greater than 2 km per kilometer square, and low fracture density area, lower than 2 km per kilometer square. As you can see, the high density area is in this area, which indicates the permeable zone, and these permeable zones become a transport that make the geothermal fluid in this central area of the Mount Gede transport or flow to the northeast of the area, and this is also indicates the northeast area of the research area are the discharge zone, and this is also in the evidenced by appearance of the manifestation, the MG1 and the MG2. Okay. Okay, let's go to the geochemistry analysis. In the geochemistry analysis, we are supported by the all incoming geothermal geochemistry spreadsheet to help our analysis. And as you can see, this is the water geochemistry analysis first. There are three manifestations that the pH is neutral, and if we input it to the bicarbonate chloride sulfate and the natrium kalium magnesium ternary diagram, we know that the Mg1, the Mg2 in the bicarbonate chloride sulfate is dominated by bicarbonate water, indicates an upflow zone in the northeast area. And then the Mg3 have a fluid type sulfate water, which indicates the upflow zone. And the Mg3 is in the central area of the Mount Gede. And then if we input it to natrium, kalium, magnesium, the three manifestations are categorized to become immature water, magnesium rich, which indicates there are some mixed by the groundwater, the local groundwater. And this is normal because in our area there are two groundwater basins, the Sukabumi and Cianjur groundwater basins. That means that in our research area, the groundwater itself is near the surface. So the manifestation got easily mixing from the local groundwater. Okay, let's go next. And this is the results if we input it to ternary diagram. As you can see, the Mg1, Mg2 in the bicarbonate, peripheral water, then and the Mg3 in volcanic water. Other than the manifestation, we can ignore it because it's just cold water and surface water. And as you can see in the natrium, kalium, magnesium ternary diagram, all of the manifestation inside the immature water zone. Okay, next to the geochemistry analysis, the gas analysis. There are two geothermal manifestation gas that are the fumarole manifestation at Wadon and Leeutic crater. And it shows, if we input it to this ternary diagram, the natrium, helium, and argon ternary diagram, there is no indication of gas originating from magmatic gas, but the Mg9 and Mg9A is unique because tend to contain helium, which indicates the presence of crustal element in the formation of geothermal gas. And this is normal too, because the Mount Gede Pangrango is formed due to the result of the subduction process in the Java, because the Indian oceanic plate below the Sundaland continent, based on the tectonic theoretically, Darman and CD 2000. Okay, next the isotope analysis. The isotope analysis is the objective is to know about the source of the manifestation. Are the manifestation come from purely from the geothermal water, or just mixing from the meteoric trend line? And as you can see from this diagram, all of the manifestation is tend to mixing from the meteoric trend line. But just the Mg8, as you can see, because the Mg8 manifestation has an enrichment of 18 oxide, this indicates that the manifestation is purely from heated geothermal fluids. And coincidentally, the Mg8 is categorized as superheated steam. The superheated steam is because the manifestation surface temperature is very high. The surface temperature is 170.2 degrees Celsius, and this is a very high temperature manifestation. But this is also very good to us because we can determine the geothermal reservoir temperature. So we are using the geothermometer gas hydrogen argon formula from the Giegenbach and Gogwal 1989, that the geothermal reservoir temperature is 290 degrees Celsius. Okay, next. Okay, so from all of the geochemistry analysis, the water, the gas, the isotope, we can do some further analysis to the geoindicator. We are using all of these elements and to know about the direction of fluid flow. And theoretically, the fluid flow in the geothermal is the geothermal fluid will flow from the upflow zone to the outflow zone from the Nicol zone. And from this table and our analysis, we can know the direction of geothermal fluid flow in the Mount Gede is from the Mount Gede crater in the central area to the foot of the Mount Gede to the Cipanas area. So the Cipanas area become the discharge zone of this in this geothermal area, and this is also supported by the emergence of the appearance of the manifestation of the bicarbonate hot spring, the Mg1, the Mg2. That means that in the northeast area, the Cipanas area is the outflow zone. Okay, this is our final results. So to strengthen our analysis, we overlay the geoindicator and the fault feature density analysis. As you can see, this is the lineament, and some fault in our area. And then in this orange area, this is the high feature density area, which means that this area is the high permeable zone. And the high permeable zone become some that can make the geothermal fluid easily to flow from the outflow zone to the outflow zone, and then the outflow zone indicates characterized by the geochemistry analysis, also the geoindicator analysis, and then to the outflow zone, the Mg1, the Mg2 in the Cipanas area, which means this area is the discharge zone, and this is also supported by the bicarbonate hot spring in this area. Okay. Okay, this is the conclusion and some recommendation in our research to the further and future analysis or development in this geothermal area. The conclusion is The outflow zone is in the area around the crater of Mount Gede to the body of the volcano, while the outflow zone is at the foot of the volcano, as evidenced by the result of the geochemical analysis of indicators. And then the FFD analysis also strengthened this analysis, and we know that the FFD and the geochemistry analysis geoindicator is correlated well. And then we can know the FFD that the direction of geothermal fluid flow from the heat source upflow zone also flow due to permeable rock, permeable zone, the high fracture density area, lineament with the southwest to northeast pattern, geological structure that cause the foot of Mount Gede become the discharge area. And then this are some recommendation. In the Mount Gede itself, it still needs exploration drill data, because this helps us to interpret the geological structure and also the alteration type in the subsurface. And also we need some geophysical studies of gravity in this research area to know about the structural control in our geothermal field regarding the relationship to subsurface of geological structure. Okay, we are very thank you to the committee and the participant to have some time to hear to our research. And we know that the Mount Gede is also one of the hot topics in the geothermal, because this area is also have been tendered. And we are very thank you, and we are very happy to discuss. So maybe everyone can have some question if there are any question in the Q&A session. Thank you. Good day. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, everyone.
Hi, what a great honor to be here. Thanks to the chairman of this session. So on behalf of my colleague, I'm here today to proudly share with you our project. Our lab is currently working on a specific geothermal project here in Indonesia. Although the objectives vary within each person, ours is to develop integrated methods for reservoir temperature estimations. One of the methods used in our project is a geothermometry, so-called multi-component geothermometry. This figure is, I assume, already known to all of us. So in a geothermal system, reservoir is one of the main elements. With many different aspects we have to consider, estimate, and calculate in the reservoir, temperature is undoubtedly one of them. Talking about reservoir temperature, especially for geochemists, we often think of a way of estimation with least effort and cost. Geothermometry has always been preferred for evaluating favorability of a geothermal system and obtaining as soon as possible the reservoir temperature. Considering temperature will be most likely measured frequently during the whole development and also production process, a new perspective of geothermometry wouldn't be hurt to be explored more in pursuance of a more reliable method that yields better result. Resuming from my previous statement on our lab's project, this particular work that we do is actually not included in the project itself. However, the method is indeed what we are using for the project. So what we do here in this work is we try to apply this method to a different geothermal field. Two purposes we are seeking are comparison and evaluation of its reliability, being it here refers to the multi-component geothermometry. Our work is conducted in Rajabasa geothermal field. It is a very fine area along the beach, full of friendly people, good food, and not crowded, which are all a researcher is asking for. Lampung province, where Rajabasa is at, has quite complex structures and geological history, since Rajabasa itself is thought as a post-caldera volcano inside a caldera margin. The lithological compositions are basaltic to andesitic lava, pyroclastic breccia, and also tuff. Two main structures are northwest-southeast trend parallel to the Great Sumatran Fault Zone and also north-south trend. Now allow me to explain a bit more details on the method that we used. So the definition of geothermometry is not something unusual for us. However, I'd like to emphasize the importance of geothermometry. We rely on geothermometry due to its expectation to give us a reservoir temperature as precise and reliable as possible, mainly with minimum data. Up to date, we recognize these first four types of geothermometry. But have you ever heard about the fifth one, the multi-component geothermometry? Here, I'll be focusing on comparing these two, solute and also multi-component geothermometry. When geothermometry are applied to estimate the subsurface temperature, a basic assumption is that temperature-dependent chemical or isotopic equilibria prevail in the source aquifer. Further, the approximation is made that chemical and isotopic reaction do not significantly modify the composition of the fluid as it ascends from the source aquifer to the point of sampling. Equilibrium between mineral solution or solute-solute is assumed for geothermometry to be applied. Unfortunately, in reality, it is almost impossible to avert the effect of near-surface reactions and mixing dilution process of fluid as it ascends to the surface and reacts with different rocks. With its other limitation on the temperature range, we turn to multi-component geothermometry to try tackling these limitations. It is believed to be beneficial for our work because it considers full chemical analysis, surface processes, and it is applicable to any geothermal systems. Unlike solid geothermometry, multi-component one uses not only chemical composition of water or gas as the input parameters, but also mineral saturation indices. A computer simulation program called IGOT was developed to automate this method into a practical software tool. It is chosen considering the improvement of temperature predictions by using full chemical analysis of water while taking into account of all possible surface processes. Looking at this flowchart of IGOT simulations, we instantly realize what differs it from solid geothermometry. The core of the software is essentially a homogeneous geochemical speciation algorithm solving mass balance mass action equations by Newton-Raphson iterations. Using complete fluid analysis, the saturation indices of minerals or log Q over K are obtained from the computed ion activity product or Q and thermodynamic equilibrium constant or K for each mineral. Data for computation of activity coefficients together with equilibrium constants for aqueous complexes and minerals at various temperatures are read from an external thermodynamic database. The program allows for simultaneous regression of multiple waters, automatic reconstitutions of the fluid compositions, and also estimations of reservoir temperature by numerically assessing the clustering of computed mineral saturation indices. Moving on to the sampling points, please take a look at this figure. So water and gas samples are obtained from each manifestations. Few of the physiochemical characteristics are written here too. Based on the compositions of major anions and cations, we try to estimate the temperature from solid geothermometry and then use the multi-component geothermometry as an evaluation method. The upper left figure displays the water type from all of the collected samples. From here, we choose the most fitting sample for solid geothermometry calculations. Within many variations of solid geothermometry, we decide on using these two geothermometry after some trials, errors, and considerations. The value that we obtain here is approximately 200 degrees Celsius. Meanwhile, we also use CO2 gas geothermometry since our gas data quality is pretty good too for geothermometry. The value from CO2 is a tad higher than the solid geothermometry, which is about 260 degrees Celsius. So going ahead on the multi-component geothermometry, although what I'm showing here looks like something simple, but believe me, it is not. The process can be briefly explained like this. As I've mentioned previously, this method uses full chemical analysis of water samples to compute the saturation indices. Here it is represented as log Q over K of reservoir minerals over a range of temperature, for example, 25 to 300 degrees Celsius. The saturation indices are then graphed as a function of temperature in degrees Celsius, of course, and the clustering of log Q over K curves near zero at any specific temperature is inferred to yield the reservoir temperature. Now let's talk about the result. We take a single viewpoint of sample SA4, and to remind you, it's on Gunung Botak on the southern part of Rajabasa, as shown on this tiny upper right figure. We have compositions of water and gas from Rajabasa as known input parameters. I said known since we recognize the value from our own calculations. Then the mineral saturation indices are originated from the thermodynamic database that we use, which is called Soltherm H06. We run all of those data in IGOT and obtain huge number of numbers as the result. They are then put in a chart like this in order to be understood easily. So please take a look at the curves, the table of the solid geothermometry calculations, and also the mineral listed. Let's focus on those three things. The clustering of the curves referred as the estimated temperature. IGOT also calculates the solid geothermometry shown on this table. We can briefly compare the result based on this figure only. The minerals here I choose based on the estimations from the database, so they are regarded as unknown parameters. At the end, from here, we obtain a value of 270 degrees Celsius. Several seams were evaluated to estimate reservoir temperature based on saturation indices of a group of minerals. Best matches of known temperatures were obtained by taking the temperature at which the absolute value of median of computed saturation indices is minimum after applying an optional elimination algorithm to select a certain number of best clustering minerals. The temperature estimations can be based on given suite of specific minerals or applied blindly using all minerals available in a separate thermodynamic database. The median of the absolute values of saturation indices is then evaluated at all temperatures. The temperature at which the final median value is at minimum is then inferred to be the reservoir temperature. The temperatures at which other statistical parameters are at a minimum, for example, mean, standard deviation, and mean root square error, are also computed to provide information on the quality of the clustering. In the case of perfect clustering, these other statistical parameters become zero at the same temperature, and therefore their values can be used to further assess the degree of confidence in computed reservoir temperature values. The value from this step is similar with the previous one, which is 268 degrees Celsius. So we're almost done, so bear with me a bit longer. Our task now is to discuss these two geothermometries. We know the solid one is easy, it's simple, and it doesn't take much time. Then why do we need to consider including multi-component one? Well, although it's complicated, I'm being completely honest here. Yet it's more reliable because of all optimization processes leading to the end result. Since it also uses complete fluid analysis, we make sure that all possible parameters and processes are included in the estimations. Now, there are three big questions that we have to answer here. Number one, are they a standalone program? No. Number two, can they support each other? Yes. And the last one, number three, can they be combined? Yes, absolutely. So finally, we arrived at the end. I list some important points from this talk. I really hope you can gain some insights and even new knowledge from it. At last, I welcome any questions, comments, and suggestions. All of them are greatly appreciated, and thank you so much.